Welcome back to Trig Notes 5.1 Part 2. Looking at this next example, if I'm trying to solve for the exponent here, I'm trying to figure out how to make a 2 and a negative 4 have the same base. Well, right away I know that 2 raised to the second power is 4, not negative 4. So I may be thinking, how do I get this negative 4 to occur? So maybe I'll do 2 to the negative 2 power. Well, that actually is negative 1/4. So there is no number that I can raise to 2 to get a negative 4. So therefore, for this problem, this is going to be a no solution. 2 raised to no power is going to get me a negative 4. Next concept we're going to take a look at that deals with exponents is interest. We're going to look at two different types of interest formulas. So let me write those out here for you. A equals P times 1 plus R to the over N raised to the N times T power. And the other one is PERT. A equals P times E raised to the RT. So notice in your explanation over here, it's telling you what each of the variables stand for. A is the account balance, so the money that you have in the account after it's earned all of the interest. P is the principal, or the initial amount of the investment. So if you put $100 into your savings account, and after maybe 2 years you have $150, 100 would be the P, 150 would be the A. N is the number of compoundings per year. We'll take a look at those in just a minute. You'll notice that it can be yearly, semi-annually. If it's yearly, it's 1 time. If it's semi-annually, it's 2 times. If it's quarterly, it's 4 times. If it's monthly, it's 12 times. And that's about as often as you're going to see compounding happen. We'll keep explaining this in just a moment down here. Finishing the rest of this off, R is the interest rate as a decimal. So if it's 5% interest rate, it would end up being 0.05 as the interest rate. And T is the number of years that your money is left in this account for. Okay. Looking at this problem here, or this form here, A and P are still the same thing. A is the amount in the account, P is the initial amount that I've invested, R is still the same, it's the interest rate as a decimal, and T is still the same as well. The only difference is that we have now an E here, and E is the natural, it's a number, it's just like pi is 3.14. E is 2.718, and keeps going on and on and on. And this table down here is going to show you how you get that 2.718 ... So let's look at that. So like I said a minute ago, the 4 typical amounts of compounds, or how often we're compounding our interest, would be yearly, semi-annually, which would be 2 times a year, quarterly, which would be, and I wrote that down wrong. I had it written down right the first time, but I went back and changed it. Quarterly would be 4 times a year, and monthly would be 12 times a year, every month. So if you were to plug into your formula here, a 1 plus 1, if your interest rate is 1, let's just say for example, over 1 compounding, and 1 times 1, you're going to get 2. If you plug in your number of compoundings to be 2, you'll notice here if I just change this to a 2 and then 1 times 2 is 2, I'm going to get 2.25. Keep going, change the number of compounds to 4 times a year. 1 plus 1/4 raised to the 4th is 2.4. Change it to 12. 1 plus 1/12 raised to the 12th is 2.6. And this is if we're going to be compounding much more often. If it's weekly, it's 52, because there's 52 weeks per year. So we notice we change to 52 and 52. We get that 2.69. If it's daily, that's 365. So that would be 1 over 365 raised to the 365. You're going to get a number that's 2.7. We're getting closer to that natural base number, which we said before was E was 2.718, and it keeps going on and on. And this is how they're getting that. This chart is showing you that. If it's hourly, 365 days times 24 hours gives you that 8,760 that you'll notice that they've used here, 2.718. And then every minute, you would multiply this then by 60, and you would then get 2.71829, and if it's every second, again you'd multiply again by 60, and you'd get this number here, and again this is your E. And e is just like pi. It is a number. You have an e on your calculator that you're going to be using to compute these problems. But again, e is the number 2.7182824, and it keeps going on and on. So the more compoundings that we make, you'll notice we're getting closer and closer to this 2.718 ... And that's where the PERT formula comes in. You're going to be using this e when you find that you are continuously compounding the interest. Continuously over and over and over and over and over again. Okay? So you have to recognize, when do you use this form of the formula? You only use this form when it's compounded continuously. You use this one when you're told the number of compoundings, when you're told that it's yearly or semi-annually, quarterly, or monthly. Those are going to be, like I said, the typical 4 that you're going to use. Let's take a look at an example. It says a total of $1,200 is invested at an annual interest rate of 9%. Find the balance after 5 years if it is compounded quarterly, monthly, and continuously. So for the first two problems, because we're told the number of compoundings would be the n, quarterly would be 4, monthly would be 12. So for the first two, we're going to use the formula a equals p times 1 plus r over n times n to the t. We'll use that for a and b. When we get down here for part C, when it says continuously, you have to use the PERT formula. A equals P E raised to the RT. Let's go through and identify our variables. The initial amount that we invest, our P, is $12,000. Our interest rate as a decimal would be 0.09, and our time would be 5. So when we compound it quarterly, our n is going to be 4. So let's plug into our calculator, or into our formula first and then into our calculator. 12,000 for the P, 1 plus r over n. R is 0.09 over n, number of compoundings is 4, raised to 4 times 5. Be careful when you use your calculator to get this answer. You need to figure out what this number is first. 1 plus 0.09 divided by 4. So let's do that. I get 1.0225. Now, that's the exact value. There's no more decimals that are going on and on. If you find that your decimal keeps going on and on, you want to store that answer in your calculator. And then I also just did this math in my head. 4 times 5 is 20. So now I can actually type this into my calculator. When I do that, because we're dealing with money, we'd round to 2 decimal places. We would get $18,726.11. So again, I'm rounding it to 2 decimal places because I'm dealing with money. That makes sense. If I start off with $12,000, I get 9% interest rate after 5 years. I should have more than my initial investment. Okay, look at monthly. So we're going to use the same formula, but we're just going to change the number of compoundings to 12. So this would be 12 times 5 out here. Now figure out what 1 plus 0.09 divided by 12 is. This time again it's a decimal, which it should be. But again, I'm not rounding that. That's the exact value of it. This is 60. Times it by 12,000. And when I do that, I end up with $18,788.17. Now notice that my answer was higher. That's good. The more often your interest is compounded, versus 4 times a year or 12 times a year, the higher amount of money you should earn. So I should have a greater value for this one than this first problem, because this was only compounded 4 times a year, whereas this one was compounded 12 times a year, monthly. So I'm earning more interest on top of interest that I've already earned. Now because it says continuously, that's when we use the PERT formula. So plugging into my calculator, I would do A equals 12,000 E raised to the 0.09 times 5. And again, I would make sure that I know how to type this into my calculator. So type into my calculator 12,000, then the E is on the graphing calculator, it should be in the very first row, the row that starts off with a second. If you go all the way down to the LN button, right above that you should see an e to the x. So you're looking for the LN button. Right above that button you see an e to the x. So you'd want to hit second LN, which would give you this. So in your calculator it's going to look like this. 12,000 and then e raised to, and then parentheses already inserted for you. So 0.09 times 5 gives me $18,819.75 when I round it. Again, no surprise here that my answer was bigger than the previous one because I'm compounding my interest much more frequently than I did in my previous problems. Alright, let's take a look at a story problem here. We're talking about in 1986 a nuclear accident occurred at Chernobyl in what was then the Soviet Union. The explosion spread toxic radioactive chemicals over hundreds of square miles and the government was forced to evacuate. If this equation here would represent how much of this toxicity was still in the air after 10 years, I want you to graph it from the interval of 0 to 100,000, where t represents the year that this explosion occurred. How much of the radioactive chemicals will remain in the year 2010, and how much will remain after 10,000 years. So here's what we know, is that year 0 is 1986. Year 2010 then, since 2010 and 1986 is 24 years apart, this would be year 24. So what I would recommend is that you pause the video and you input this into your graphing calculator where your t is really your x and your p is really your y, and change your window to these scales. So again, pause the video and set up your calculator first and input this into your calculator. Okay, so now that you've actually looked at the graph, you're going to see that this is what your calculator should be showing you if you set up your window correctly. What I really want to know is how much of the chemical is left over 24 years after the explosion occurred. So there's two ways I can do this. In my calculator I can hit calculate and then it'll come up as value. And then when I type in x equals 24, my calculator would give me the number of the y value is equal to 9.99. Or I could type out in my calculator, not in the graphing window, I could do 10 times 1/2 raised to the 24 divided by 24100, and I get 9.9. But since we used our graphing calculator already, let's use our calculator. So that means there's 9.99, I don't know what the units are, it doesn't give me units here, if it's grams, if it's milligrams, whatever it may be, left of this chemical in the air 24 years after the explosion. We want to know how much of this chemical is left in the air after 100,000 years. So again, go back to your calculator and hit calculate and plug in an x equals 100,000, and you would find that y would be 0.56. So there'd be 0.56 left of this chemical in the air 100,000 years after the explosion, which the government then has deemed to be enough that it's safe for people to come back in after a certain time.